Thanks for showing up late night for this tutorial. So I can see several names from my section and few names from other sections as well. Okay, so good to see that. So let's start. So today, I'm going to do some problem solving on the electrostatics part of our EE340 course. And this will cover our chapter 4, 5, 6 of Sadiku textbook. And these questions, they have been taken from various resources. And I really hope by the end of this tutorial, it will benefit you. Okay, so and also in the while we do the problem, if you have any question, you can raise your hand and I will try to answer the question while we go through the problem. Okay. Although the session is 1 hour, let's see by the end of 1 hour how many problems we will do. Because when I make the presentation, I doubt that it will finish in 1 hour. Okay, so let's start. So this is the first problem, and this problem is mostly based on the students' understanding on the Gauss's law of electrostatic and the uniform charge distribution. So the problem says that you have a spherical volume charge density distribution, and this exists in free space. So free space, that means our epsilon is epsilon naught, and the charge distribution is something like this. So rho v is equal to rho 0, and this charge distribution, it exists only between A and B. So as you can see here, so this is the spherical volume charge distribution. So it's a spherical volume, but it is hollow at the center. And the charge distribution is only in this dotted region. So between A and B. And this has the charge distribution of rho 0. And outside it is 0. That means outside there is no charge distribution. And this is your the permittivity is epsilon. Okay. And also if you see, rho 0 is a constant. So rho 0 is a constant. Now what we need to do is we need to use Gauss law, and we need to derive the expressions for the electric field in 3 regions. That is in this region, in this region, and this region. So where R is less than A, so that means in this region, the hollow part, then between A and B, where we have our charge density, rho v, and outside. Okay, so how are we going to proceed? We are going to use Gauss's law, and we will now enclose our spherical volume distribution, this our whatever problem space that we have in our hand, we will enclose it in a Gauss's surface. We will enclose it in a Gauss's surface, and we apply the Gauss's law. Now, how are we going to do? So first, okay, so first, now we are in this region. So this A is for R less than A. So how are we going to do? So since this is a spherical distribution, so first what I'm going to do, I'm going to put a small Gauss's surface, and the Gauss's surface will again be a spherical shell. It will be a spherical shell, and this will cover its radius is rho, and this will cover the region of our interest. And our region of our interest is, sorry, not rho, r. And the region of our interest is r less than a. So therefore, the radius of this, which is r, will be less than a, so that our Gauss's surface is inside this hollow region. Now let's apply Gauss's law. So what does the Gauss's law says? It says that closed surface integral d bar dot ds bar is equal to the charge enclosed. Now, if you see here, now inside this spherical surface, is there any charge? Is there any charge, or is there any charge density here in this surface, inside this green spherical surface? No, because according to the distribution, the charge is only in this region. The charge is 0 here, the charge density is 0 here, and the charge density is 0 here. So therefore, the charge which is, or the charge density which is enclosed in this spherical shell, that I am showing it with this yellow color, here, this yellow color, there is no charge in here, right? And that's why, if you see here, your charge enclosed is 0. So therefore, if this is 0, if the right hand side is 0, then the left hand side must be equal to 0. So therefore, your d bar will be equal to 0, and therefore your e bar will also be equal to 0. Okay, now the next case. So our next case is when we are in the region of this, where my r is between a and b. R is between a and b. So that means I am in this region. So again, what we are going to do here, in order to find the magnetic field, I'm first going to decide my Gauss's surface. And again here, my Gauss's surface will be a spherical shell. But this spherical shell, I'm going to put it in my region of interest. That is between A and B. And this radius will be A. Okay, this radius will be A. Now, let us apply the Gauss's law. So the Gauss's law says that the closed surface integral d bar dot ds bar is equal to the charge enclosed, right? And now the left-hand side, I can simplify it. As we all know, closed surface integral d bar dot ds bar, I can simplify it because d and ds bar both are parallel, and therefore I can get closed just d outside, closed surface integral of ds. And what is the area of this spherical shell, this green spherical shell? The area will be 4 pi, the radius of the spherical shell, which is r. Sorry, this should not be a. This should be r. So it is 4 pi r squared. So this is how we get the left-hand side. Okay? Yes.
Here, how did you know that the boundaries for rho is from A to R, not from A to B, because it is in between?
Yeah. So
in other words, how to determine the boundaries of rho?
See, now we need to find it in 3 regions, right? Where r is less than a, where r is between a and b, and where r is greater than b. That means what will be the
yes.
here? Okay, so now
in this, the integral.
Yeah. So now what we need to do is, if we are interested in this region, then we will put a Gauss's surface inside this region. And this r is a variable. Okay, this r is a variable. And this r can take value anywhere between a and b. Got it?
So
now I am interested in this region. I'm interested in this region, right? So therefore, I put a Gauss's surface, which is my green color spherical shell, in between this region. And I'm saying that this radius is R. So this R can take value anywhere between this A and B. But so since this is a variable, I'm keeping it anywhere in this region.
oh, okay, got it. Okay.
Got it? Okay. Now let's go back. So therefore, we got the left hand side, which is typical. So d times 4 pi r square, because 4 pi r square is the surface area of my shell, the surface area of my green shell. Because for a spherical shell, the surface area is 4 pi r square. Now the thing is, how can I find the charge enclosed here? How can I find the right hand side? So now we need to now go here and we need to see that how much is the charge enclosed here in this spherical shell. How much is the charge enclosed here? So inside the spherical shell, if you see here, this is the complete volume. Can you see this yellow one? This is the complete volume. Now, if you notice, first, let us see, do we have any charge inside here? Do we have any charge inside this green spherical shell? Yes, you guys can answer me. Do we have some charge here?
Yes, we have.
Yes, we have some charge. And where is that charge located? We have a partial charge. See, and the partial charge is here. It's only here. See, can you, only here. This red color, which I am drawing, only here is my partial charge. Whereas the yellow part, it doesn't have any charge. So now what I need to do is I need to find the charge. So how I am going to find the charge? So I know it very well. The charge Q is equal to integral over the volume rho v dv, correct? Now the good thing is this charge rho v, which is here in this red region, this charge rho v is rho 0, and which is a constant, right? It's a constant. So therefore, I can say that Q is equal to integral V rho V dV. So since rho V is a constant, I can take rho V outside and integral over the volume dV. So now we just need to find the volume of this red region. We need to just find the volume of this red region, because this is the volume where rho v exists, and yellow is the region where rho v doesn't exist. So therefore, you have to multiply your rho v with only the volume of this red region. Now, how can you find the volume of this red region? I can find the volume of the red region as, I can find it as 4 by 3 pi r cube, which is the volume of my complete sphere, which is enclosed in my Gauss's spherical shell. It's the complete volume. From here, if I subtract 4 by 3 pi a cube, which is the volume of this yellow part, the volume of this yellow sphere, because yellow sphere doesn't have the charge. So if I subtract the complete volume of my sphere, so complete volume of my sphere is the volume which is enclosed in my green spherical shell, which will be 4 by 3 pi r cube. And from here, if I subtract the one which doesn't have the charge, which is the yellow one, is 4 by 3 pi a cube. This will give me this volume. And I do not need to go and do the integration because my charge density is a constant. So I can just take it outside the integration and I can just make use of the formulas that we know to find the volume. And this is how we got here. See, it is rho 0 times 4 by 3 pi common r cube minus a cube. And therefore, now if you do the simplification, so 4 and 4 cancels, pi and pi cancels, and then d, the relationship between d and e, we know it very well. D bar is epsilon e bar. So therefore, e bar will be your d, which is this one, rho 0 r cube minus a cube over 3. Epsilon naught is coming from here because this is free space. So epsilon naught and this r square going on the right hand side. So this will be the electric field which will exist inside this region where you have a charge of rho 0. Clear? Now let's take the third case. So third case, where now my R is greater than B. That means this region, all. So therefore now let me put again another Gauss surface. So again a spherical shell in the region of interest where R is greater than B, and let it be of radius R. And R is variable. It can take values anywhere from B to infinity. It is greater than. Yes.
From where AR came, Doctor?
This AR?
Because we have AR in the, yes, because we have AR in the right hand side. And if we want to take it to the left hand, we have it in the left hand side and we want to take it to the right hand side. Don't we divide by one?
No, AR, okay, because in this say tutorial, I thought you guys are aware of this from where AR is coming. See, this AR is coming from our prior knowledge, okay, the experience that we have. So what did we learn about in electrostatics? That if a charge, and if this charge is a positive charge, then the electric field which is created by this positive charge will be radial in this direction, correct? So it will be radial.
Okay.
In R direction, if I put it in the spherical coordinates. So with that experience, we are coming and solving this problem. Okay. Now in this problem, again, see the region between A and B, between this region between A and B, you have this charge and it has a charge density which is positive. That means it's a charge density which is positive. So therefore, again, if we go and use our Coulomb's law, you can go and use our Coulomb's law, then what you will get, you will see that since it's a positive charge density, so therefore your electric field should go away from that charge in a radial manner, So therefore, before even starting our solving, we can just from our experience says that my D bar should be dr AR. That means it should have only one component, and that component is the AR component. So this is coming from our experience. And now how to find this unknown thing, this unknown part, this unknown part dr, then we use the Gauss's laws to find that unknown parts. Got it? So here, this is the unknown part.
Yes, yes.
Find. And in fact, this, and then once we find this D, then we just substitute. So if this is D, then your E bar will also be ER, AR. So we got the electric field. So we got this magnitude from the Gauss's law, and then we put back the AR vector. Clear? So now let's continue.
Yes, yes.
Yeah. Now in the third region, how are we going to do in the third region? We are going to put a Gauss's surface of R here. Okay. And then we will apply Gauss's law again here. So in this, again, the left-hand side will be D times 4 pi R square as the case of B. But here, remember, your R will be greater than B. And here the R was between A and B. Is equal to now the right-hand side. Let's see for the right-hand side. Now, how much? So let's see what is the region here. So the region enclosed in this Gauss's surface is this complete region, right? This complete yellow region. Complete yellow region. Now we need to find the charge enclosed in this region. Now, again, as we know, out of this region, only this region has the charge. See, only this region has the charge. This. So therefore, now how to find this charge enclosed? Again, the same idea that I told you for the second case. So the charge enclosed is integral over V rho V dV. So this is nothing but integral over V rho 0 dV, which is rho 0 times integral over V dV. So now what will be the volume of this red region? So the volume of this red region, can I say that the volume of my red region is 4 by 3 pi B cube? That is the spherical volume of this sphere, you know, where I'm showing you the spherical volume of this big sphere whose radius is B, minus 4 by 3 pi A cube. Why? Because this is the volume of my inner sphere of radius A. So if I subtract the volume of my sphere of radius B, and if I subtract the volume of the sphere A, if I subtract the volume of the sphere A of radius A from the volume of the sphere of radius B, then I will get this red region volume. And that's why this will be here. So therefore, if you see, it is 4 by 3 B cube minus A cube times rho 0. And this is 4 times 4 pi R square. Again, 4 pi cancels. And therefore, you get rho 0 times B cube minus A cube by 3 epsilon R.
R or R squared, Jackson?
Just a second. B cube 4 pi R squared 4 by 3 B cube minus A cube times rho 0 epsilon over. This should be R squared. I think, sorry, there is a typo error here. Okay. So it is 4 by 3 B cube minus A cube. So it should be R squared here. Okay. So this should be R squared. Okay. So 4 cancels, pi cancels, and D will be B cube minus A cube times rho 0 over 3 epsilon R square, and then AR. Okay. So this should be R squared. Done? So this is how you can find for different regions. Okay. Now, this was the case where, if you remember, my charge density was constant. My charge density was constant. Now, suppose if my charge density is not constant, then how you should do? If the charge density is not constant, then how you are going to do? Then you need to be careful a little bit. So this is an example, although this is a very long example, but I will be focusing on the first part, okay? Because of the time, I will be focusing on the first part. So again, it says that you have a spherical volume and it is placed at origin and has the charge density distribution this. So rho V1 is K1R and it is in the region from 0 to H, and then it is 0 elsewhere. Now, do you notice this one? So this is important. See, R. That means my charge density is non-uniform. This is important. You need to be careful. So therefore, whenever you want to find the charge, you cannot take it outside. You have to keep it inside the integral and then do the integration. Okay. So now, what do we need to do this? We need to find the electrostatic field at this point. The point is this. So we need to find the electrostatic field at 0, 0, H. Okay. The second part, we will talk about it later. First, let's look at the first part. So this is the spherical volume and we need to find the electrostatic field at 0, 0, H. That means just on the surface of this spherical volume. This is what we need to find. Now, how to solve it? So if you see here, how it was done. So this is your spherical volume. Rho V is K1R. And this is my spherical region. And this is placed at origin. And I need to, so this is the spherical region. And I need to find the value of my electrostatic field at height h. So height h is on the surface. Okay, just remember, height h will be on the surface. It will be here because this is your volume. So height h is nothing but it is the radius of the spherical volume. And how we got it? Because we know rho v is K1 times R for R is less than H. That means the charge is already enclosed in a spherical volume and that spherical volume is between 0 and H. That means it's a spherical volume, that it's a sphere, and that sphere has a radius of H, and that sphere has a volume charge density of this value, K1 times R. So now apply Gauss's law. Again, we know it very well, just to share with you, because so D1 bar is again will have only one component, dRAR, because the charge is here, so the field will be radial like this. It will be radial. So therefore, we need to find only this one. So now I need to enclose it in a Gauss's surface, right? Now, since I need to find it at a particular point, right? So since I need to find it at a point which is this one, H. Then rather than using a variable R spherical shell as your Gauss's surface, rather than using variable R, I will use a fixed R. I will use a fixed R and I will use that Gauss's surface, which is the same spherical shell which is enclosing your volume charge, your spherical volume. So I will not make it variable. I will evaluate Gauss law exactly at R is equal to H. So therefore, this Gauss's surface, its radius is h. Okay, exactly here. So I will not make it as a variable. So in this case, my left-hand side will be d1 times, instead of 4 pi r square, which is the surface area of this spherical shell, which is our Gauss's spherical shell. Instead of 4 pi r square, it will be 4 pi h square, because I'm evaluating it at a fixed r is equal to h. So this is how I got the left-hand side. Very straightforward as the previous example. Now the right-hand side is the key. So in the right-hand side, if you see how I'm finding the charge, I'm using charge is equal to integral over v rho v dv. And now I cannot take rho v outside because my charge density is non-uniform. So if you see here, it is K1R, which is rho v, and dv, because it's a spherical volume. So what is the elemental volume? It is r square dr sine theta d theta d phi. And where r goes from 0 to h. Why? Because only your charge is in this region from 0 to h. And theta and phi will take the complete ranges, because it's a spherical, it's a spherical volume. So theta will take from 0 to pi, and phi will take from 0 to 2 pi. And you are keeping your charge density inside. So this will become r cube. And therefore, what you will get? Yes, so you will get, the direct answer is written here, but you can do it properly. So it will be K1. This will be r cube. That means that will be r power 4 over 4 from 0 to h. Then sine theta will be what? Integral of sine theta is minus cos theta. And theta is from 0 to pi. And then t phi, there is nothing. So its integral will be just phi from 0 to 2 pi. And if you do the simplification, you will see that you will get 4 pi k1 h to the power of 4 over 4. So this is how you have to find the charge when you have a non-uniform charge density. So the right-hand side is the key. So now, then do the simplification. 4 pi cancels, h square, this will become h square. So what is left? It is k1 h square over 4 times ar. So let me just write it first here, step. So d1 is equal to k1 h square over 4 times ar. This is your answer. But since the point, what was our point? Our point was here, right? And this point was 0, 0, h, this point. But this point is in Cartesian coordinate. It's not in cylindrical coordinate. So therefore, or spherical coordinates. So therefore, I got the the electric field or electric flux density in the spherical coordinates, but I want to see how it will be in the Cartesian coordinates. Now, what you can do is you want to find it at h, this h. So just by analysis, you can say, so what will be the electric field direction in Cartesian coordinates at this h? Yes, can anybody tell me? Without even going to the
question again, Doctor.
Without even going to the transformation of the unit vectors, we can straight away say. So what my question is, let me just do it again. So what my question is, we want to see at this point 0, 0, h, what is the electric field of this volume, spherical volume, only here. We don't want a generalized expression. This is a generalized expression where r can be any way.
Along AG, it should.
Want only in this direction.
Should be along AZ.
AZ. That's why your AR is directly written in AZ. So this doesn't require the unit vector transformation. By the way, even if you use the unit vector transformation, you will get the same answer. But sometimes, guys, always going and using the unit vectors transformations is not good. Sometimes, you have to think a little bit and then you will get the answer in no time. So here, because I'm just restricting my direction to this H, and I know this H is along the Z-axis. So therefore, I can simply replace AR with AZ. And this is the electric field that I will see at 0,0H, which is my Cartesian in the Cartesian coordinates. And this will be the electric field because of this spherical volume. Okay. So this is an example where we have used a non-uniform distribution, non-uniform. Okay. Now this second part, I think I will leave it. Maybe if time permits, I will do the second part, because the question was you have two different distributions and you need to find the electric field at 0,0H. So that means you have to use the superposition principle. First, you find the electric field due to this, then the electric field due to this, and then first electric field due to this at this point 0,0H, then electric field due to the second charge distribution at the same point 0,0H, and then add them. So what I did is I did the half part. We used this spherical volume and we found its electric field at this point H. Now for the second spherical distribution, if time permits, we will come back and we will do it. Okay. So let's go to the next ones, because this is the second one. Let's go to the third one. Yeah. So this is an example where you have a semicircular ring. So you have a semicircular ring, and this ring is of radius A, and it is carrying a uniform line charge distribution rho L. So it is carrying a uniform charge density. And what is that line charge density? Rho 0. And since it is a uniform line charge density, automatically you should know that this is a constant. Then the semicircular ring is placed in the XY plane. So it is in the XY plane with its center being at the origin. So the center is at the origin. Now, what is the electric field at the origin? So what will be the electric field that you will experience if you are standing at the origin due to this charge distribution? So how are we going to move here? Because we do not have any, say, expression that we can directly use, because we have the expression of electric field for an infinite line. But here the distribution is totally different. So therefore, what should be the best approach for this kind of problem?
We find the charge for the half ring by integral rho L dl. Then
yes.
we use the
so which law you're using?
What is it?
Which law we should use here? Should we use Gauss's law? Should we use Coulomb's law?
Yeah, we use Coulomb's law for this.
Yeah, we use Coulomb's law. So this is the thing, guys, when the question appears to you, I always tell my student, just, pause for 1 minute or 2 minutes and read the question and first find what approach you are going to take. Because in the previous examples, we used Gauss's law. And why Gauss's law came in my mind? Because here symmetry is there. That means your electric field or your magnetic flux density is only a function of R. And therefore, it's much easier to put it in a Gauss's surface and then apply Gauss's law and get the field. But in this problem, there is no symmetry. That means your electric field generated by this, it's very difficult for me to visualize. It's not so straightforward for me to visualize. So therefore, in such cases, it's always good to go for Coulomb's law, as you have just now mentioned. Okay. And then, as you mentioned, it's correct. You can take a small dl volume here and then integrate it over the complete half ring. And this is your observation point. That's it. So once the approach is right, then getting the solution, it will be no time. So what I'm doing here, so if you see here, I'm taking this as my observation point, and this is the general expression of Coulomb's law, rho L dl r bar over 4 pi epsilon r cube, and r is what? The distance vector. And what is the distance vector? So this is my small dl. So this is my small dl, which I'm assuming. This small dl, this I'm assuming, and the distance of this small dl length to the observation point is my distance r, or my distance vector r bar. And what is this dl? Because it's, say half a ring. So the best coordinate system to fit this is, what will be the best coordinate system?
Cylindrical.
This is x, this is y, and the z is coming out of our screen. So the cylindrical is better. So therefore, I'm writing this dl in terms of cylindrical coordinates. So it will be r d phi, but since we know that the radius is a, that's why it is a d phi. And this is what I'm defining r. Now, what will be this vector r bar? Can you tell me? What will be this vector r bar? The vector r bar is direction is always from the source to the observation point. So if this length is a, but I'm going in the opposite direction, right? So therefore it will be minus a arrow, because my arrow direction is this direction. Remember, my z is coming out. So this, my z is coming out of the screen. So this xy plane is, where you can see your row. So it's a sort of a row plane. So your arrow is in this direction, but my distance vector r is in the opposite direction, and it has a fixed distance. So going from here to here, it's a fixed distance a. So that's why it is a. And since it is opposite to arrow, that's why it is minus a. So once you get this, it's just straightforward. You have to substitute here. Your rho L is rho 0. Your dl is a d phi. Your distance vector r is minus a arrow over 4 pi epsilon. This is the distance vector q, which is a q. And then what will be the units here? Because it's the integration is with respect to d phi. Now the units is a little bit important. You have to pay attention to the units. You are in cylindrical coordinates. So it is with respect to phi. So you need to define the phi units. So remember, phi angle is always measured with respect to x-axis. And it goes in this direction, like this. So phi takes 0 to how much?
2 pi.
This is the range. So now since phi is defined from here, but our ring is from here. So therefore our unit should be, so what is this ring? What is the value of phi here? Phi is equal to pi. This is phi is equal to pi. And then coming back here is phi is equal to 2 pi. So this is the range, pi to 2 pi. And this is where students usually does, say mistake in selection of the this limits of your phi. So it is from pi to 2 pi. So pi to 2 pi. Now you simplify it, then you will get as what you will get. Integral phi is pi to 2 pi rho 0 a square, so minus a square over 4 pi epsilon a cube times a rho, correct? Times d phi. Am I right? Yes. Now, these are all constants. This can go outside. So therefore, your electric field will be integral, sorry, it will be, this all will go outside. So minus rho square, minus rho 0 over 4 pi epsilon. You will have a here because a square and this will cancel. Now integral pi to 2 pi a rho d phi. Now here is the catch, guys. You need to be careful here. And I have emphasized this several times in my class, that can you take the a rho unit vector outside the integral when the integral is with respect to d phi? You need to be careful. And this, mostly this situation will come, especially with a rho and d phi in our problems. And the answer is no. I cannot take a rho outside the integral and just say that it is 2 pi minus pi and therefore it is pi. No, it's wrong, because a rho, unit vector a rho is a function of phi. And how do you know that it is a function of phi? Just try to visualize it from the Cartesian coordinate system. So from the Cartesian coordinate system, just try to transform this in Cartesian coordinates, then you will know. So the best thing is, if you have a doubt, then try to visualize this a rho vector in Cartesian coordinates. And if you see, the a rho vector in Cartesian coordinates is cos phi ax plus sine phi ay. So see, it's a function of phi. So it cannot go outside the integration. So you need to be careful with this one. And in such case, the integrations are usually done by converting a rho into the Cartesian coordinates and do the integration and get the answer. Obviously, your answer it will be in Cartesian coordinates. So if you can leave it with this Cartesian coordinates answer, but suppose if the answer is in cylindrical, then you have to again change back to cylindrical. But most of the time, we don't ask these kind of transformation again back to cylindrical. So this integration is done here. And then as you see, what we get it as minus 2 times a. And that's why I am now substituting this complete integration with minus 2 times a. And this is your answer. Okay. So keep this in mind, because here again, it's highly probable that, students do mistake here. So you need to be careful here. Okay. So next problem. So this is the problem of potential difference. How do you apply the expression for the potential difference? Remember, we have the expression of potential difference, which is VAB is equal to minus integral A to B E bar dot DL bar. Remember, this is the potential difference. The potential difference that is created due to the presence of the electric field in that region. So this is an example where it is showing how to apply this expression. Yes, someone was asking something? No? Okay, so what is the question? So the question is saying that you have, it's a free space. It's a free space and you have an infinitely large plane sheet of uniform charge density rho s. And it is placed on the YZ plane. So if you see here, this is a plane now because Z is coming out of our screen. So this is a plane and this is an infinite plane and this plane carrying a uniform surface charge density rho s, which is 2 nanocoulomb per meter square. And now we have 2 points, which is point A is here, which is 750. So x is 7, y is 5, z is 0, and minus 500. So x is minus 5, y is 0, and z is 0. So since both the points are in the xy plane, because z is 0, can you see here? So they are in the xy plane. So this is the point A, this is the point B. So that's why we are seeing the problem in the xy plane. Now we want to find the potential difference VBA. So going from B to A. So what will be the potential difference if we go from B to A? What will be the potential difference? So now in such kind of problems, so where we need to go from point B to point A, you know it very well that in the potential difference, you can take any path you like because it is independent of the path. So you can go in this direction, or if you want, you can go in this direction, or if you want, you can go in this direction. It's all up to you. Now, it depends on which path is easier for you to evaluate. So this is what you need to find. So first, let's find what is required. So first, to apply this expression, which is VBA, is minus integral a to b e bar dot dl bar. Just take a note, it is b to a, not a to b. So therefore, b is the lower limit and a is the upper limit. You need to find first electric field. So let's find the electric field. And the electric field, and how is the electric field now? The electric field in this region, because here you have the point B, and you all should also know the electric field in this region, because here you have your point A. And we know it very well because you have a sheet, you have an infinite sheet, and this infinite sheet is responsible for this electric field. But unfortunately, you know, on the either sides of the sheet, the electric field will be different. The magnitude will be the same, but the direction will be the different. So that's why I'm dividing this problem into 2 parts. See, 2 and 1. 1 is this region, 2 is this region. Because if you are in this region, the blue region, light blue region, what will be the electric field due to an infinite sheet? It is there in the formula sheet that we always provide. So E1 bar is rho s over 2 epsilon times AN. AN is the normal vector, which is normal to this surface, which is this one. This one. This one. This is your AN. If you are in this direction, if you are here in the region 1. So therefore, rho s is 2 times 10 power minus 9 over 2 epsilon 0. So what will be the AN vector? Anybody can answer this. What will be the AN vector in this problem?
Depending on the region.
Yeah, no. I'm asking in our problem statement, because see, we know the coordinates. This is x, this is y, and the one coming out of the screen is z. So in this case, what will be the AN?
AX.
AX. So yeah, so you have, because AN, this is the generalized formula. Now we are applying this generalized formula for our problem statement. So in our region 1, AN is this direction. So what is this direction? This is nothing but the direction of x. So because this is my AX, so my AN is my AX. So that's why I'm replacing AN with AX. So this is the electric field in this blue region. Now in the pink region, if you are in the pink region, according to the formula, you know it very well. AN is if you are in pink region, this is how the AN is defined. if you are in the pink region, according to this general formula. Now, looking at our problem statement, what is this AN here in this region? What is this direction? Minus AX. So therefore, in this region, magenta or the pink region, your normal is minus AX. So therefore, your E2 will be minus, the magnitude will be the same, AX. So here, the electric field magnitude, here the electric field magnitudes are the same, but the directions are different. Here, the electric field is in this direction, and here, the electric field is in this direction. So once we got the electric field, we apply this formula. So VBA is B to A. Now, how should we move from B to A? Can we move in this direction? Or should we move in orange direction? Or should we move in this blue direction? Now you have to evaluate, and based on how is your electric field is in which direction? It is in the AX direction, AY, AZ, so that it will be easier for you, because sometimes the dot products can become 0 and you will get the answer quickly. So if I go from here to here, unfortunately, it will be difficult because my electric field direction is in this direction. So this green and this orange, it is very difficult for me to evaluate. But that I can use this blue direction. It is much easier. Because first, let me move from B to here, and then I can move from here to here. So out of these two lines, this is, if I say this is line A, and if I say this is line B, the contribution of line A is, so can anybody tell me?
0, because the dot product from the electric field and the direction is 0.
No, this A, the contribution of A will be 0. Contribution of A will be non-zero.
B will be 0.
Yes. So the contribution of A will be non-zero. Why?
Yes.
Your electric field direction and the direction of your DL along which you will be moving, they are parallel. So therefore, the dot product will not be 0. But for B, it will be 0 because your DL direction will be along Y, which is dy, and your electric field is in X direction. So therefore, the contribution of B will be 0, no contribution. So therefore, you're only left to evaluate this. And to evaluate this, you only require X, which is from here, which is -5, to here, which is 7. And from -5 to 7, you cannot evaluate directly from -5 to 7, because from -5 to 0, you have a different electric field, and from 0 to 7, you have a different electric field. So therefore, you have to divide this into 2. How? Instead of going from B to A, or instead of going from -5 to 7, first go from -5 to 0, and then go from 0 to 7. So when you go from -5 to 0, you will have E2. So this will be, okay, let me just write it. I think, guys, it's time, but just give me few minutes, I'll be done. So your VBA will be -5 to 0, E2 bar dot DL bar. Okay, then minus integral 0 to 7, E1 bar dot DL. So this will be equal to minus integral -5 to 0, E2 bar dot, what will be DL here? DX AX. It will be DX AX. And here
also DX
bar DX AX, also DX AX. So therefore, E2 is already along AX direction, E1 is already along AX direction, so AX dot AX will become 1. So it is simply the magnitude of this multiplied by dx, which is here, and simply the magnitude of E1 multiplied by dx, which is here. And then you just simplify it and you will get the answers. Okay, so this is how you can apply the idea to find the potential difference. And you need to just identify the correct, path to move. And you will see that the problems in problems, a complicated path will never be given. The paths will be quite simple paths, where the dot product with the electric field in half of the path will be 0, like this. And the dot product here will be 1. So it will be easier to evaluate. This is, always keep this in mind, because we will not give evaluation in this path is not an undergraduate level type of question. Okay. So I think, guys, it's 9 o'clock. Now it's up to you. If you want me to continue, we can continue for few more minutes, or if you want to conclude, we can conclude. What do you say?
Can you, Doctor, send us these slides?
Just a second. What did you say?
Slides, send us these slides.
Slides. Let me think about it, because I think those students, maybe for those students who have attended, for them I can send the slides, but let the other students say, though, since you have put efforts, it's easier for it will be better for me to, those who are not from my section, just drop an email to me, and then I will